Alright, hi folks, welcome back to Physics with Captain Rod. So the purpose of this video is to discuss how equivalent capacitances are calculated for a parallel combination. So what we're looking at here is we've got some sort of DC voltage source, a battery, connected to a pair of capacitors of value, capacitance values C1 and C2. And here we have a switch in the circuit. We're going to imagine the switch is closed now. And when we close the switch, remember that the positive terminal of this battery will attract electrons. So electrons are going to want to move in this direction, leaving us with positive charges here and here. Now, on the other side of the circuit, electrons are going to march this way, leaving us with negative charges here and here. So these capacitors now are going to be charged to a value, let me call this one Q1 and Q2. Now, voltages are very important in any of these circuit problems. So I'm going to take a moment here and color code the voltages. So this is the high voltage, or the higher voltage side of the circuit, I should say. This is the positive terminal. And this would all be a constant voltage or constant potential. This is due to the fact that this is all conducting material. And remember from my IFAX video, the conductor itself is an equipotential. And then we have the other side of the circuit. I'll just leave it black, but this would all be at one potential. So this problem now really only has one potential difference, which is the potential difference of the battery. The circuit diagram would look something like this. Right? Again, this is the symbol for potential difference, DC potential difference. This would represent the voltage across these terminals. And we'll make it look a little cleaner here. So here's our capacitor that I called C2. And up here is the capacitor that I called C1, which has a charge Q1 on it and a charge Q2 on this guy, charged to the polarities shown. So color coding that picture again, over here, this is the high voltage or the higher voltage side of the circuit, and this would all be one potential because it's conducting material. And a very important thing to recognize is there's just one color change here. Black, red to black, red to black, red to black. This is a property of what's called a parallel circuit. Very important that parallel circuits have constant potentials across them. The voltages across anything in parallel will be the same. Now, million-dollar idea here is, can we discover a single capacitor that would be equivalent to these two? And that's what would be called the equivalent capacitance of the circuit, or of the system, I should say. C equivalent. Oops, I can write that a little better. This would be charged to this polarity. Color coding this here. This is the higher potential side of the circuit. All right, so for series capacitors, the idea of equivalent capacitance comes from the sum of the voltages. The voltages across the capacitors add to the voltage across the battery. But for the parallel combination, that's not true. The voltages are the same. The equivalent capacitance comes from the idea of the charges. As we look at this picture, we have a charge here. We've got a Q1 here, a Q2 here, and I just call it Q for the charge on this capacitor. Anybody want to guess as to the relationship between these three charges? Yeah, it's additive. Effectively, this single plate is the sum of these two. So what we can say is that charge 1 plus charge 2, whoops, I can write that a little better, is equal to the charge on our equivalent capacitor. And now remember, capacitance is defined as charge over voltage. So charge can be written capacitance times voltage. So this term can be written C1 times the voltage represented by black to red. And then this one can be written C2 times the voltage represented by, again, black to red. And then this one, looking over here, can be written C equivalent times the voltage represented by black to red. Yeah?
Just to clarify, for this context, for what we're talking about today, when we prefer to charge, we're talking about an imbalance of
yes. When a capacitor is charged, what we're talking about is a charge imbalance. More electrons on the left than we have on the right, but the net charge on this, if we added them up, would be 0. And the voltages are the same. They're all red to black. So what we get is that the equivalent capacitance is just the algebraic sum of the two capacitors when they're in parallel. Hopefully this makes physical sense, because capacitance, one of the primary factors is surface area on the capacitors. Basically, when you hook these in parallel, you have the surface area of this plate added to the surface area of this plate, adding to the capacitance of the system. So another thing to point out is that had we put another capacitor here in parallel, that would just add a C3, and another one would add a C4, and so forth. So the purpose of this video is just to go through and explain how you find equivalent capacitors in parallel, and it's as simple as this. In parallel, the capacitances just add. Now, in order to apply this, you have to realize, well, when are they in parallel? And the answer is anytime the voltages are the same across them in configurations like this. Okay. So I think I'll just end that video here and start another one with some numerical examples.
So weren't they additive in series as well? So is it the same principle for both, or is there a difference?
They were additive in a reciprocal sense. So remember, for series, we had 1 over C equivalent was equal to 1 over C1 plus 1 over C2. So there's two different ways they add. They add like this in parallel and like this in series.
Gotcha.
Okay. All right. We'll take a look at some numerical examples.